be learning about what is science, along with some of the terms used to define what we talk about when we talk about basic science. You will also be learning about the scientific method, density, and something known as pseudoscience. I want you to keep in mind, though, that these PowerPoint slides are designed as a supplement to the reading. There will be questions on the assessments that are not covered in this PowerPoint presentation that are covered in the text. In this section, you will be learning about quantitative descriptions, including objects, properties. You will learn how to quantify properties. We will learn about the different measurement systems, standard metric units or SI units, and the metric system, understanding measurement and collecting data. You will also learn about the application in the scientific method, investigations, scientific laws, and the difference between models and theories. Objects are things that can be seen or touched, such as a tree, and properties are qualities or attributes characteristic of an object. The tree is rough or brown or tall. And then we could also use something known as a referent, which is a comparative property in other more familiar objects. In other words, we wouldn't just say blue. The referent would be the thing that we are referring to, the sky. And so sky blue, sky would be the referent. The problem with referring to things simply based on reference and properties is that language can be subjective. In other words, you may say it's warm when it's 80 degrees, but somebody in Alaska may say it's warm when it is 60 degrees. And so we need units in order to be able to quantify things. Quantifying properties involves using measurement with basic units. For example, degrees or feet or meters. So when quantifying, we go through 3 steps. We compare the referent unit to the property being described. We follow a procedure specifying how the comparison is done, and then we count how many standard units describe the property under consideration. But essentially what we're doing is we're creating a quantified number with a certain referent unit. In this case, the referent unit would be something such as degrees, and the number would tell you how many of those units, for example, 50 degrees or 7 feet. Just saying that a desk is 4 would not tell you anything without the referent unit of the desk is 4 feet, which is why you need both. We basically use 2 measurement systems today. The first being the English system, which is used only in the US, versus the metric system, which is universally used, including in the US. The English system was based on using parts of your body, such as the tip of your thumb would equal an inch, or a foot would equal, well, about a foot. However, this was later standardized based on the metric system. The metric system was established in the late 1700s in France, and it has 7 basic units. These 7 basic units are from the 7 fundamental properties, the first one being length, which is the meter, mass is the kilogram, time is the second, electric current would be the ampere, temperature would be Kelvin, the amount of a substance would be a mole, and the luminous intensity would be candela. Fundamental properties are simply units that cannot be broken down any further. For example, if we were talking about surface area, it would be a length times a width, right? Meters squared. So it can be broken down into meters and meters. And so the fundamental properties are essentially for length, The unit is the meter. Mass is the kilogram. Time is the second. Electric current is the ampere. Temperature is Kelvin. The amount of a substance is a mole. And the luminous intensity is candela. One of the advantages of the metric system would be the ability to quickly find out any calculations based on moving the decimal place. For example, if we had a meter, 1 meter, and we had 1,000 of these meters, you would move the decimal place over by 3 to get a kilometer. So 1,000 meters would be 1 kilometer. However, if you did 1/1000th of a meter, it would be a millimeter. And so a lot of these terms you've used today, even though you say we don't use the metric system in the US, you've probably heard of a gig or a terabyte. These are all metric prefixes. You might have even heard of nanotechnology or used milliliters. These are all metric prefixes that we use in the US as well. One of the great advantages of the metric system is the ability to quickly convert either in your mind or on paper by simply moving over a decimal place based on if it's getting larger or smaller. For example, at the very top you see a meter, and then you see right underneath it they have highlighted the 1 decimeter. 1 decimeter is essentially a tenth of a meter. In other words, there are 10 decimeters in 1 meter. If you see that decimeter, it's been broken down even further into a series of centimeters. In fact, there are 10 centimeters in 1 decimeter. You see the centimeter has been broken down further so that there are 10 millimeters in 1 centimeter. However, keep in mind there's 1,000 millimeters in 1 meter, 100 centimeters in 1 meter, and 10 decimeters in 1 meter. Understanding from measurement. Measured information is known as data, which is very important in science, and we'll get a lot more into that later. We also will be looking at ratios and generalizations, and what's called the density ratio, symbols and equations, and problem solving made easy using a series of steps. Data is simply the measurement of information. And let me say that again. Data is simply the measurement of information. And this information can be used to describe objects, conditions, events, and changes. Density is simply the ratio of how much of something there is per unit of volume. In other words, it's the ratio of mass and volume. And its formula is simply density with the symbol rho, which looks like sort of like a P, equals mass, usually in grams, divided by volume, usually in centimeters cubed. However, this can also be in units of measure of liquid, such as the liter. And this particular ratio is specific to a specific material. In other words, if you had 5 grams of gold, or if you had 250 grams of gold, while you'd have a lot more money, the density of the gold would be the same, no matter how much gold that you have. A good example of it would be a ball bearing. They're very heavy. That would mean they have a high density versus something like paper that's going to be a lot lighter. Symbols and equations, the book goes into in great detail. However, it's important to know the basics that symbols, they represent quantities or measured properties, and equations take those symbols together and they create mathematical relationships between properties. They describe properties, define concepts, and specify the relationship between these properties. One of the topics that the book covers in a lot more detail is this idea of proportionality and relationships between different properties. The book talks about specifically 4 different proportionalities. However, here it only talks about 2, and one of them being what's called a direct proportionality. An example of that would be where something increases, the other thing increases as well. For example, as you are a child, as your age increases, your height would also increase. So if one thing increases, the other increases, or if one thing decreases, the other factor decreases as well. An inverse proportionality, however, is whereas if one increases, the other would decrease. An example of this also would be, say you have a full gas tank and you go on a trip. With the amount of miles that you go, it's increasing as you're driving. The amount of gasoline in your tank would decrease. And this would be inverse proportionality. As one increases, the other decreases. And these proportionalities can be looked at as equations if you use something called a proportionality constant that's going to relate these 2 factors or quantities. There's also what are called numerical constants that will not change. They are specifically constants. In modern science, which really began about 300 years ago, we have these 2 scientists, Galileo and Newton, which really kicked off the idea of modern science with their ideas and their ability to experiment and test these ideas. However, they were not the first people to think about science. That goes back to ancient times, in BC times, where scientists were not necessarily called scientists, but were called natural philosophers. They had ideas about nature that they were unable to test or experiment with based on the amount of information and equipment that they had at the time. One of the ways that we go about testing our ideas is through something called the scientific method. And if you've ever done a science project in middle school or high school, you probably were required to show that you used the scientific method. This involves really 5 steps. The 6th step is not necessary if you were able to fulfill what you needed to without having to re-examine your hypothesis. Essentially, the first step is to observe some aspect of nature. The second step is to propose an explanation for something observed. Maybe it's this. And then use that explanation to make a prediction or a hypothesis. And then test the hypothesis with experiments or more observations. And then either step 5 could be draw a conclusion or modify your explanation and hypothesis in order to be able to go to step 3 again and make a new prediction. The problem with the scientific method is that science has a huge span, anywhere from the idea of working with nanoparticles all the way up to working with cells in a sterilized environment. And how we address different aspects of science and technology is different for every facet of science. But overall, the things that they have in common is the fact that we are collecting observations, we're developing explanations, and then we are testing those explanations. Some of the key terminology in science are, as far as the explanations and investigations, are as follows. We have the hypothesis, which is a tentative explanation for some observation. There's the experiment, which is a recreation of an event or occurrence to test a hypothesis. There's a controlled experiment, which compares 2 situations with all factors alike except for one. A good example of this would be if you're testing a new fertilizer on a crop, you wouldn't just give it to the crop and see how it does, because it could be that this year we had lots of rain, or this year there was a series of pest infestations that destroyed the crops. That had nothing to do with the fertilizer. It simply had to do with the conditions of that time. So what you would do is called a controlled experiment, where you have two fields that everything is the same, from the soil content to ideally the amount of sunshine, and if they're right next to each other, you would assume they would have the same bugs or pests. So the control group would be the fixed group that does not have the fertilizer, but the experiment will be that one thing that's different, the one thing that differs from the control group. So you could say, compared to the control group, the fertilizer showed that there was an increase or no increase, or even that it could have potentially been a bad fertilizer for that particular crop and actually had a decrease in growth. Some terms that people often confuse are scientific laws, models, and theories. Laws are important because they are the relationship observed to occur in nature time and time again. Without the idea of laws, these things would still occur. The laws were just developed to help explain nature and not vice versa. In other words, if you look at Charles' law, there's a relationship between temperature and pressure in gases. This can be observed in a hot air balloon as the temperature is increased and the pressure in the gases would also increase. Models are a description of a theory or idea that account for all known properties. There are several different things that could be considered models. You could have a physical model, a mathematical or computer model. It can be based on a sketch or even an analogy. They're useful for regimes too small or too vast for direct observation, such as the solar system or an atom. Theories are broadly based set of working hypotheses. They're based on considerable experimental support. They form the framework of thought and experiment, and they often change more often than laws. Laws rarely change. However, theories are a work in progress. There's also something known as a conjecture, which would be an idea that it's not based on several observations like theories. For example, you could say, you left out the fruit and now there's bugs. Therefore, bugs grow from fruit. That would be a conjecture, but it would not be a theory, because as you observed time and time again, you would not see this relationship. Pseudoscience is referred to as a false science. Pseudo means false. It's misleading and often absurd claims of scientific results. However, many people have fallen victim to pseudoscience. Taking a drug that has not been approved that is supposed to help you lose weight by increasing your metabolism, or something along those lines where you want it to be true, and so you believe it without the scientific background that shows that it's true. One of the ways that you can test it involves looking at a series of these 5 different steps. You need to ask yourself, does the person making the claim have an academic and scientific background? In other words, has this person just been living in his parents' basement, or has he been at the National Academy of Sciences for the last 20 years and has been doing research on this topic? Is there a history of review by scientific peers? In other words, has he published this data and come under scrutiny, or have there been other publications that follow based on his particular area that he has published, or she? And also, has this work been shown at scientific institutions and organizations? Has he gone to conferences and shown examples of this or given talks based on this? As mentioned, the peer-reviewed journals, similar to the history of review by scientific peers. And then, does the claimant have something to gain? In other words, is he selling this and he will make lots of money, or is this something that was made because this scientist from the National Academy of Sciences realizes that we have an increasingly obese population and has therefore developed this drug? Or is he just going to be moving out of his parents' basement into a really nice yacht? These are things to ask yourself. What does the claimant have to gain from this particular information? As previously mentioned, a lot of information and background information on what is in these PowerPoint presentations is covered in the actual text in the chapter reading, and I recommend that you absolutely read that because it will really help fill in any of the gaps you have in your knowledge or ability to comprehend what they're talking about, and it uses certain examples. For example, if you're not understanding density, there are several problems that you can do that will help you understand density. This also, as mentioned twice, has many things that are going to be on the assessments that come from the text that are not covered in the PowerPoint presentation. So you really, really want to read through that.